We're starting Chapter 13, which is the last chapter in Unit 3, and Chapter 13 is about experiments and observational studies. So we're going to look at experiments and observational studies, discuss the difference between the two, as well as how to set up a good experiment and what is required to do that. But first, we're just kind of going to look at an overview of an experiment and observational studies. We're going to start with observational studies. So observational studies are where researchers observe responses and don't assign them. So they're not assigning any type of a treatment or variable involved. This is good for discovering trends and possible relationships between different variables. There are two different types of observational studies. The first is a retrospective study, where researchers first identify the subjects and then they look at past data or responses from history. So they're just looking at data that has already been collected. So they had no impact on collecting the data. They are just looking at what past data is telling them. Because they are based on historical data, they can often have errors because you don't get any say in how the data was collected. So if the data was not collected correctly, then there could be issues. The other type of observational study is a prospective study. This is when you choose the subjects in advance and then you collect the data as the events unfold. For example, if doctors were comparing how premature babies grow and develop compared to babies that are delivered full term, they might identify babies that were born premature and babies that were born around their due date, and then watch how they grow and develop over time. So they're watching the events unfold. This can be a little bit better because then you know how the data is being collected, and so you can avoid bias and mistakes. Observational studies tell us if there is an association between two variables. That's it, just if there's an association. They cannot give us cause and effect, and they cannot give a generalization of the population. It's not random, and it doesn't necessarily represent the whole population if it's not random, because you are picking who you are looking at. It's a very narrow association between the variables that it can give you. And once again, it cannot give you a cause and effect relationship. For example, a recent medical study showed that of men who have had a heart attack, those with a certain protein are more likely to have a second heart attack. We don't know if the protein is causing the heart attack or if the first heart attack causes the protein and then that's why you have the second heart attack, or there could be a lurking variable and which cause both. Perhaps these people are smokers and therefore having a heart attack is more likely if you are a smoker. Maybe smoking causes that protein. So you don't really know. All you know is that there's an association between having a heart attack the first time, having this protein, and then having a second heart attack. In an experiment, it's a little bit different. An experiment is a study design that allows us to prove cause and effect relationship. So once again, in an observational study, you cannot prove cause and effect. In an experiment, you can. An experiment is actually the only way to prove a cause and effect relationship. The reason why this is possible is because you are applying treatments to different groups and then comparing the results of each group. So you are actually implementing a treatment onto subjects. So the cause and effect relationship can only be applied to the population at hand. So if only teenagers are tested, the results cannot then be applied to middle-aged or elderly people. It could only be applied to teenagers. Experiments can draw stronger conclusions than sample studies, like what we did in Chapter 12, or observational studies. So, sampling variability and statistical significance. Different groups have different means, so averages, even if the treatment has no effect. So, even if you are testing a new medication for headaches, if the medication doesn't work, you're going to have different responses from group to group no matter what. We expect to see that. Randomization will cause the means to be different, at least slightly, and this is what sampling variability is, the fact that each group will be slightly different. That's sampling variability and completely normal and expected. In fact, it would be probably more interesting if there was no difference from group to group. Because we expect there to be a difference, we need to know how big of a difference will show that the treatment actually had an effect. So if the headache medication actually is working, how large of a difference are we expecting to see from the group where it worked to like a group who didn't get the medication? Later on in the year, we'll be able to actually give more of a numerical value to statistical significance, but for now, all we're really looking for is if the differences are larger than what we would assume. If we assume to have some variation, and then all of a sudden that variation is much larger than we were expected, then we know that the differences are because of the treatment, and those differences are called statistically significant. So when those differences are bigger than what we expect, that's when it is statistically significant. Again, let's look at how big that difference has to be. So how do you know when the difference is big enough? Again, when we start testing data in the second semester, we'll be able to actually put more of a numerical value on this and actually see how you can determine if there is a difference or not. But for now, let's look at like a simple example. If you flip a coin 100 times, you would expect to get heads 50% of the time. What might make you think that that coin is not fair and that it's weighted to land one side or the other? If you flip it and you get 54% of the time that it lands heads, we're probably going to be okay with that. That seems reasonable, that if you flip a coin 100 times, you could end up with 54 heads. That's not out of the realm of possibility. If you were to flip it and you were to get heads 94% of the time, that's probably a little bit more interesting, and probably indicating that the coin is weighted, and we would consider this to be statistically significant. You kind of have to be able to draw that line, though. I use two kind of extremes here, one really close to 50 and one really far away. So what happens if it's 61%? Is that enough to make you think that that won't happen? And that's kind of when we get into a little gray area. For the record, 61% would still be unusual. So let's look at what type of statistical study was used, because so far we have learned about sample surveys in Chapter 12, observational studies, where you're just looking at the data as it unfolds or on data that has already been collected, and then experiments, where you're applying a treatment and seeing what happens. So, first example, Roy's Toys received a shipment of 100,000 rubber ducks from the factory. The factory couldn't promise that all rubber ducks are in perfect form, but they promised that the percentage of defective toys won't exceed 5%. Roy wanted to get an estimation of the percentage of defective toys, and since he couldn't go over the entire 100,000 ducks, he took a random sample of 10, and he found that 10% were defective. So what type of study is this? It was a sample study. It was a survey. He surveyed 10 ducks to see if they were defective or not. Is this study appropriate for the statistical questions it's supposed to answer? And in this case, no. Now, I know we talked about sample size, and it's not necessarily the sample size, but 10 out of 100,000 is really not enough. We would want to do more than just 10. So because of how small the sample was, we can't actually answer the question. We would need to look at more than just 10. If you were to look at 100, that would probably be good enough. Looking at our next example, a nutritionist had a hypothesis that eating a single banana an hour before a marathon can improve performance and reduce running time. To test her hypothesis, she randomly assigned a group of 360 men about to participate in a marathon to two groups. One group was instructed to eat a single banana an hour before the race, and the other group was instructed to eat nothing during the few hours before the race. After the race was done, she compared the average running times of the two groups. This is an experiment because she actually applied a treatment, eating the banana or not eating the banana, to two different groups. The nutritionist found that the average running time of the group who ate the banana was 5 minutes shorter than the running time of the group who hadn't eaten the banana. What valid conclusions can we make from this result? Here, the results suggest that a male runner will likely run a faster marathon if he eats a banana an hour before the race, as opposed to eating nothing. Now, the only thing about this conclusion is that we can only compare eating a banana to eating nothing. Looking at another example, Alma has developed a new kind of antibiotic. For the antibiotic to be sufficiently effective, it has to kill at least 90% of bacteria when applied to a harmful bacteria culture. She applied her antibiotic to a petri dish full of harmful bacteria, waited for it to take effect, and then tried to estimate the percentage of dead bacteria in it. She took a random sample of 300 bacteria and found that 94% of them were dead. Then she calculated the margin of error and found that the true percentage of dead bacteria is most likely to be above 90%. This is an observational study. She didn't apply a treatment. In a sense, she kind of did here, but not entirely. When you're doing an experiment, you have to apply more than one treatment to more than one group. In this case, we're only looking at one group. She gave the bacteria the antibiotic and then watched what happened. So it's an observational study. It would be a prospective observational study instead of a retrospective here. Is this study appropriate for the statistical questions it's supposed to answer? And no, because the study didn't have a treatment or a control group. Because there was only one group, that's what made it an observational study and not an experiment. If she would have had a control group or a second treatment group, then it would have been an experiment, and then we could have had more of a cause and effect relationship. But because it was an observational study, because it was only one group, we can't actually answer the question that she's asking. Looking at our last example, the mayor of Statville has to decide how to allocate her education budget between the two high schools in town, Stat Sticks and Datum High. To decide which school deserves a bigger proportion of the budget, she went over the grade sheets of the students from both schools in the past 5 years and analyzed the data. This, again, is an observational study. It's an observational study because she's just looking at data. She's not applying a treatment and she's not performing a survey, so this is an observational study. This would be a retrospective study because she's looking at data over the past 5 years, data that has already been collected. She ended up finding that the overall grade average of Stat Stick students is 4 points higher than the overall grade average of the students at Datum High. What valid conclusions could she make? The only conclusion that she can make is basically what she said. Students from Stat Sticks in the last 5 years had higher grades on average than students at Datum High. That's it, and we can only talk about the last 5 years because that's the only data that we looked at. So let's talk about what we have learned. We can recognize sample surveys because you're actually asking people, you're designing a survey and actually asking people or having them fill something out. An observational study where you are just watching data as it unfolds or taking past data and analyzing it. And a randomized comparative experiment. So an experiment, you're comparing multiple treatment groups to see if your treatment has an effect or not. These methods collect data in different ways and then lead us to be able to make different conclusions. We can also identify the difference between a retrospective and a prospective observational study and understand the advantages and disadvantages of each. And then we also know that only a well-designed experiment will allow us to reach a cause and effect conclusion. And that is because we manipulate levels of treatments to see if the factor we have identified produces changes in our response variable. That is it for tonight. I will see you guys in class tomorrow. Have a great night.